give a keynote, but also to learn from some of the other interesting talks scheduled at this conference. There's really a large amount of things happening both in quantum information and actually more in quantum sensing, and lots of new quantum developments are happening, so it's not just quantum computers, and it's really a new world out there.
Seeing the possibility of electromagnetism, cell phones, TV, GPS, etc. And it's still a subject that's continuing with new discoveries, such as photonic crystals. So quantum mechanics, just being 100 years old, really is still got some new things to go. Well, until recently, the result from quantum mechanics that got the most kind of people in the public had heard about was something called the Heisenberg uncertainty principle, which really was the thing that emerged in this beginning first quantum revolution. And another popular meme from quantum mechanics is the idea that quantum mechanics says you can leave a room by two doors at the same time, and I noticed there's actually a talk with that title in this meeting, probably tomorrow, I think. So, but in recent years, the idea that's viewed as central to quantum mechanics is being replaced by viewing entanglement as essentially the most central part of quantum mechanics. So, starting around 1980, the kind of new insights into quantum mechanics started to emerge with the discovery of topological quantum states of condensed matter. But prior to that, in the late 50s, Richard Feynman had started thinking about quantum information. He started worrying about what would happen when computers got smaller and smaller, and he saw that was going to inevitably happen until they get down to the atomic scale, and then you cannot ignore quantum mechanics. And Feynman wrote a very influential essay at the time called Plenty of Room at the Bottom, based on, there was a famous play called Room at the Top at that time. And he really has founded the ideas of quantum information that are now coming to be central. And so what's happening now is that what we're going through is the exquisite experimental, very fine control of quantum states is now the aim for the new things, a new role in quantum mechanics. In the past, maybe experiments were just smashing something and looking at the pieces that came out. Now we're trying to learn how to gently guide quantum processes to use them for practical purposes. And as you've heard, some consider this is the second quantum revolution and will deepen our understanding and the practical use of quantum mechanics and come to fruition, in fact, starting much earlier than the next 10 to the 20 years for some of the uses. So remember, let me remind you some of the issues of quantum mechanics. Originally, original ideas started before the first revolution. We have some legacy from it. Niels Bohr had a picture of the atom like a little solar system, the electron going around the nucleus, which had just been discovered, like a planet going around the sun. And the word orbit was used. When Schrödinger introduced his picture, in Schrödinger's pictures, Bohr's little clean, little planetary orbits become a fuzzy box that contains the electron. We don't know exactly where the electron is, but only it's in this box or not. So Heisenberg's uncertainty principle turned Bohr's orbit into a fuzzy cloud centered on the nucleus. But we still, in using the historical Bohr's language, we call this an orbital, and I'll come back to this thing. So atomic orbitals are essentially boxes in which we can put electrons. We neither know they're in there or out, but we can't really see them more precisely, except when they're highly excited. We could actually now get a picture of an electron orbital. In a sense, there's something called a Rydberg atom, which is actually one of the qubit structures that people are using as one of the proposed qubits. This is where I have a highly excited orbit of an electron, and there in the image you can see a hydrogen atom in an excited state of a so-called Rydberg atom. So, okay. So one of the fundamental principles in quantum mechanics is actually central to our life around us, the Pauli exclusion principle. So quantum mechanics you may not realize you'll have quantum mechanics everywhere around you because you're not really experiencing interference and other quantum effects, but indeed the reason, you may have heard that the atom is 99% empty space. And the reason when I walk on this stage I don't fall through it to the center of the Earth due to gravity is the Pauli exclusion principle. So fundamental to all the matter we have around us is the fact that fermions or electrons, two electrons don't want to be in the same place. And the law that Newton discovered, the reaction force that Newton found, that if you press down on something, it presses back on you. He just called that the reaction force or the normal force. Now we know it actually comes from quantum mechanics, and you can only understand it that way. And indeed, so quantum mechanics is, even if you're not aware of it, is fundamentally around you. And the reason you don't fall through the floor is the electrons in the atoms bound to the sole of your shoe don't want to be in the same place as the electrons bound to the atoms in the floor, and that's where the normal force comes from. So quantum mechanics has really revolutionized our understanding of the world around us and matter. So the Pauli exclusion principle says two electrons can't be in the same state, so what defines that state? In addition to its position, the state of an electron depends on the direction of its spin, because it's got a property like a little spinning top. And so it's spin, and we can put two electrons in the same box, but only if the spins point in exactly opposite directions. And we can't tell which direction they point in, but they have to be opposite, otherwise the Pauli principle wouldn't allow them to be in the same box. And this is the maximally entangled state of the two electrons. Two electrons, one has to be up and down, and the other one down, but that you can't tell the difference between the electrons. So in fact, they're actually both up and down and up at the same time, but up and down are nothing special. You could be left and right and left at the same time. So entanglement is there everywhere, and in fact in the chemical bond that holds us together. So entanglement is nothing special on the level of atomic scale physics, but we'll see that entanglement is remarkable if we can allow things to stay entangled over distances much larger than atomic scale. And that's what we're trying to do these days. So anyway, high school physics is based on putting things in boxes, electrons in boxes. But as I say, the chemical bond is essential to the matter. To bind the atoms together is essentially a maximally entangled state. And in fact, the chemical bond and the entanglement in it is probably almost all the quantum mechanics that a chemist needs to know, or possibly needed to know until recently, because the rest of it you can think of in a mechanical way as the bonds holding atoms together. So anyway, the central theme into the new approaches to quantum physics seems to be this entanglement property, and it goes back to Einstein. Entanglement is now recognized as a central property, and Einstein pointed it out. And it's viewed as the fuel to drive modern future quantum information processes. But Einstein pointed it out because he thought it was so crazy it couldn't possibly be true. So Einstein discovered an explanation a quantum mechanical explanation of the photoelectric effect, as we heard in an earlier comment. But by 1935, he kind of rejected the quantum theory intellectually. And he identified this key property of quantum theory that he felt was so weird it just had to be wrong. He called it spooky action at a distance, or in German, spukhafte Fernwirkung. But Schrödinger came up with a much more neutral word, the word entanglement, or in German, Verschrankung. Actually, entanglement is a very interesting word because every language has adopted a different root for this thing. In French, it's intrication, entanglement, verschrankung. In Kanaka, it's probably got a different root than it has in Hindi, apparently. I don't know, but it's interesting that the word for entanglement, when translated into local languages, is very variable. So around about 1935, when this happened, Einstein and Podolsky and Rosen proposed a kind of thought experiment, and in which he thought would prove quantum mechanics was wrong. It was just some approximate theory to a more deeper reality. And in fact, Podolsky, one of his collaborators, went to the New York Times and told them Einstein has disposed of quantum theory. And no country was being invaded that day. I guess the 30s was kind of a bad time for that sort of thing. But it made the front page of the New York headline, New York Times. Einstein's problem was he thought that if you have this entangled pair like a chemical bond and you measured the spin of one and the two electrons were separated over a large distance, if you measure the spin on one side and find it's up, quantum mechanics will tell you it's always down when the other person measures it. Now, to Einstein, that seemed a bit like instantaneous motion, and he knows that nothing can travel faster than the speed of light, according to relativity. Information can't travel. But in fact, it's not a violation of relativity because there's actually no information being communicated. You can take a laser pointer, a very high-powered one, I guess, and point it so it makes a spot on the surface of the moon. And as you move your hand, the spot moves faster than the speed of light across the surface. But it's not being used by anyone on the moon to signal anyone else on the moon faster than the speed of light. Okay. So anyway, let me not go through the whole thing, but basically it's a thought experiment. Einstein thought it would prove quantum mechanics wrong, but it was not possible to do that during Einstein's lifetime. In fact, it waited till after he had passed away before the experiments were really done, and starting with theoretical improvements of Einstein's objection to make it more clear what the experiment would say, would prove. John Bell introduced ideas which then were tested. Finally, Alan Aspect, the last one in the sequence, one of the people who got the Nobel Prize 2 years ago, did the test which had the feature in it that you can choose which direction, which axis to measure the spin of the electron, or the spin in this case of the photon, along, and the decision on which axis to take was taken long after the particles are separated. So unless you believe that everything is preordained, which some interpretations of quantum mechanics might say that, if everything is preordained, then all you say there's no such thing as free will, and the choice of axis to use, but it already was predetermined. But most of us kind of believe in free will in our daily life, even if there's issues in understanding how it relates to quantum mechanics. And without that, that's the one get-out clause that's left in the tests of quantum mechanics. But anyway, entanglement over long distance is fragile. That's the problem. It has remarkable effects if we can have entanglement over large distances, but it's kind of tricky to make. But with photons, which were used in Aspect's experiment, the spin is now the circular polarization of the photon, and we know photons travel a long way without decohering with their environment. We see photons from soon after the Big Bang, when the universe crystallized, when matter atoms, kind of neutral atoms, formed in the universe, and it became clear for light. The microwave background comes from 13 billion years ago. So light can travel a long way without getting decohered, and indeed, people are using this now for transporting quantum cryptography, for sending the key over and making sure you haven't been overheard. So these experiments have worked. Now, classical information is stored in a bit, which is just a switch which is on and off. But as most of you probably know, that the quantum information is stored in the qubit, which is a two-state system, which has a representation as a little arrow pointing to in a direction on a sphere. So the spin can point in any direction, and there's clearly more information than just up or down being stored in that. But you can only measure it along one particular dimension, so you could, with your choice. Okay? Now, classically, information is unaffected by reading it out or copying it, and one of the central issues in quantum information is the no cloning theorem. You can't copy a quantum bit. In fact, classical information is actually difficult to get rid of. You have to do a lot of work to clean out your mobile phone before you recycle it. But the quantum information is much richer, but is much more fragile, and it can't be copied. So but it can be teleported. So one of these, so we have the no cloning theorem that says I can't copy a qubit. But what I can do is I can move the information in a qubit by using entanglement to move it over large distances if I've got entanglement over large distances. So, for example, this is one of the things that were the idea that entanglement is a resource for quantum information comes from. If we have an entangled pair over a large distance, and I want to copy a qubit over here to over here, I carry out a measurement of the pair of qubits, the one half of the entangled one and the one over here, and depending on the outcome of that measurement, which has 4 possible outcomes, I pick up the telephone and tell the distant person what the experiment said, and then they can perform an operation on the other half of the qubit, of the entangled qubit, which will then, depending on what they were told the outcome of the experiment was, and they can recreate it. So this is one of these remarkable things, like in Star Trek, the teleportation. But it uses up the long range. You no longer have the long range entangled pair after the end of it, so the resource has been used up. Okay. So anyway, this is the idea that entanglement is the fuel. How do you produce entanglement? Any two systems will become entangled with each other if we bring them together and let them interact. But we want to actually produce this maximally entangled state, the pure Bell pair. In the chemical bond, just the energetics of the chemistry, force of putting those 2 electrons in the same place in the chemical bond forces maximal entanglement on the but it doesn't work for remote objects. To make a 100% entangled Bell pair, we start with 2 qubits in known states. We bring them together in contact with a carefully constructed quantum gate, and then we wait an exact amount of time and switch off the gate, and marvelously, if we did it exactly at the right time, they're maximally, when we pull them apart, they're maximally entangled. But it's a pretty delicate procedure to get this just right with the quantum gates. And I'll show you that the topological quantum stuff is an aim to do this in another way. Anyway, around about 1980, the condensed matter physicists who were studying matter, they kind of thought they sort of understood everything, sort of, right? They understood magnetism and superconductivity and various kinds of ordered states, and you know, when a community thinks they've basically got all the details right, nature will come along, someone will discover something unexpected and really put you back to square one and show you that there's a lot more than you thought, as in I guess a quote from Hamlet like that. So what was found in 1980 were two things which turned out to be, they were found out actually within a few hundred meters of each other in the same place, within also a short distance, a short time interval. One is in Grenoble, France. One is, of course, the quantum Hall effect that von Kissing discovered, and a more minor thing maybe was what initially was a kind of rather unexpected but unusual feature in quantum magnetism in low dimensions. So these things turn out to be a different kind of state of condensed matter in which quantum entanglement plays some kind of role, and it's called the topological states. And in the intervening years, many more kinds of topological states have been discovered, some of which have the potential for what's called topologically protected quantum computing. And we'll get to that. So topological matter differs from ordinary matter because it's got some entanglement-related properties that can be described by whole numbers. Ordinary matter might be described by, I put boring numbers like 0, 1, but 0 is actually really not a boring number. In fact, it was discovered in India way back, but it describes, 0 could describe something with non-topological properties. And the basic point is that if matter is characterized by a whole number, and in one region, and a different whole number in another region, you can't change continuously between whole numbers. There has to be a boundary where something changes, and it turns out there's often something very interesting happening at this boundary between topologically distinct states of matter. So topological properties can't change continuously, which makes their properties robust to small amounts of dirt, which is in contrast to our current silicon-based technology, which requires ultra-clean silicon wafers to be produced. The suits in the fab there are not there to protect the workers from any noxious chemicals involved in producing the wafer. They're more there to protect the wafer from any little bits of hair or spit or something falling off the workers and ruining the chip. So absolute cleanliness is needed, and topological properties have a kind of robustness. So the classic example that everyone gives in these kind of talks is classification in mathematics, which is actually the original place that topology kind of got introduced, classifying a surface by the number of holes in it. Now that can only be done on a macroscopic scale. If you actually look at a real physical surface, which is made of atoms, it's not a smooth surface that you can classify by the number of holes. And indeed, topological descriptions, they actually only work on a scale large compared to some microscopic scale, because on a microscopic scale, things are not smooth like a mathematician thinks of the topological stuff. But anyway, holes have to come in whole numbers, right? There's no such thing as 0.3 of a hole. You either got it or you don't. And Gauss, the great mathematician Gauss, he made many important discoveries, but the discovery which he found the most strange and remarkable is that the fact that the surface area of the sphere, 4 pi r squared, times the Gaussian curvature, which is constant on the surface of the sphere, 1 over r squared is equal to 4 pi. He called that his marvelous theorem. Of course, it's trivially true for a sphere, but if I change this shape into a rugby ball or a banana, it remains true. The Gaussian curvature on the surface is no longer a constant, but when I integrate it out, it always will equal 4 pi, so long as there are no holes. And this is the thing the experimentalists working in this subject can't resist showing the movie, which I will not show you, of a coffee cup turning into a donut and back again. On the donut, you can see there's the inside part of the donut, the curvature, which is the product of two radii, which are now in opposite directions on the inside, is negative, so parts of the bagel have negative curvature, which cancel the positive part. Then we have these other shapes, the loving cup and the Swedish pretzel. The real pretzel is minus 8 pi. I'm not sure what this thing is called. I've heard people suggest it should be called a California loving cup, but let's pass over that. So mathematicians love to make more general abstract versions of theorems, and indeed the mathematician Sherman converted Gauss's kind of physically sounding theorem about real surfaces into a much more abstract mathematical theorem of mathematical surfaces on mathematical spaces, and it's on, since they don't have a Nobel Prize for mathematics, it's on one of the, and you have to be young to get the Fields Medal, it's on one of the 2 Nobel-like prizes there. Okay, so in recent years, it's been realized that quantum condensed matter has these unexpected properties, and they can be associated in some sense with long-range entanglement. If I take an ordinary piece of matter and cut it in half, there's actually not much entanglement on the boundary, and it's basically the quantum state is like a product of the quantum state on the left independently and the quantum state on the right, which means I can do a measurement on the left side without it affecting a measurement on the right side. But topological matter has this kind of longer range entanglement. That means if I try to cut it into 2 bits, it resists a bit, but once I've cut it, I've got these new edge states which separate the trivial from the non-trivial world on the thing. So topological matter, trivial matter can be just thought of assembling atoms. Topological matter, you have to reassemble the quantum state inside it, and that happens at a particular point when I bring them together. So let me skip that. So, okay, what am I here for? I guess in 1981, I discovered that a chain of spins, let's go back one, that the spins are multiples of the elementary qubit spin, 1/2, so spin is actually always an integer multiple of elementary spins. Okay, so the total spin is either an integer or a half integer. And in 1981, I found that the spin 1 chain could have a novel state, which instead of looking like a load of atoms assembled in a certain way with their spins pointing up, then down, then up, then down, actually changed into what we now call a spin liquid. But basically the spins have split their spin 1 into 2 spin halves again and rejoined them with their neighbors. And the interesting thing about that is half of a spin 1 is left on either side of the system, which is a typical thing of topology. And we'll see that this picture will actually be what's one of the things which goes into the so-called Majorana qubits that Microsoft are trying to push right now. Okay, so this was kind of controversial at the time, and it had a lot of blowback, but basically it was because people were not thinking in terms of these kind of entangled structures, thinking more in terms of just reassembling the atoms in a kind of simple way. So this was very controversial, but in all science, condensed matter, we can actually got material science to make things. We can do experiments. And finally, people made this was a toy model, but people turned the toy model into reality by working out how to make interesting compounds, in this case a chain of nickel atoms. And finally, this controversial result was experimentally verified. And indeed, the fact it was controversial at the time led many people to develop lots of new techniques. So controversy is very great in science. When people disagree, that's when we make progress. If everyone is nodding their heads in agreement with something, nothing new is developed. When we disagree, that really leads to working out. Usually when we disagree, there's truth to both sides of the question, and what we find out to resolve this thing leads to progress. So controversy is always great in science because it's good for innovation. And this is the meme. The meme was this line of people holding hands. Hands usually come in pairs unless you've had an accident. But if I make a chain of people holding hands, we violate the theorem that hands come locally in pairs because I've got one independent hand at each end of the chain. And this is turns out to be the simplest example of topological matter of that. So there was my certificate. They put this toy model on it. The toy model was actually invented by other people to show up this thing. But anyway, let's move on. The most important of those two discoveries was the quantum Hall effect. And that's had an immediate technological, or not immediate, it's had a huge technological significance. The system of units is now based. The kilogram is no longer a lump of metal in a safe in Paris. It's something that's measured using this quantum Hall effect and another effect from superconductivity to make a Kibble balance. And the amazing thing that von Kissing discovered was that he did a certain measurement, and each time he measured a certain voltage with a current flowing his device worked out that the voltmeter was not deficient. They discovered they'd really found something remarkable, okay? And indeed, you can see this number that his measurements showed is just a fundamental constants times an integer, and that was actually should have been recognized as topological right away. But indeed, you've got these little, you have a magnetic field which makes electrons go around in little circles called Landau orbits. And if they're inside a region, they just go around in little circles, but if they get close to the edge, you can see the orbit will hit the edge and they'll bounce and they'll go around. And if you follow it around, you'll see at the edge, they flow around the edge in one direction only, which is a remarkable thing. You've got a kind of edge state property, which is a one-way street. And it comes with a magnetic field, breaks time reversal, which means that if I took a movie of the thing and watched something going around the edge and showed it backwards, it would be different. It would be going around the other way. So anyway, this is a remarkable thing, and it led to this, that we can have these incredibly accurate now determination of the kilogram. So a little bit after that was the fractional Hall effect, which was a remarkable thing. I don't have a pointer, so I can't really point it out, but instead of that integer times e squared over h, it was an integer, it was 1/3 times e squared over h. And the person who discovered it, and Sui experimentally, immediately had the right answer to that question, because at that time people had proved that, theorists had proved it had to be an integer times e squared over h. Unfortunately, the experiment came just after the people were nodding their heads and said, yes, we understand it. And he realized it had to be an integer times e by 3 squared over h. And immediately recognized the correct answer that this object involves fractionalization of electrons into 3 parts that can move independently with charge 1/3 inside this new material they discovered. But this is a kind of remarkable thing. Now you can see the device that this was seen in. The man who made it, who unfortunately was left out of the Nobel Prize because only 3 people can get it, would not have got a job at Intel if he submitted that as a proof of his soldering abilities or something, right? But the robustness of topological stuff make it possible to see such an effect even in this device that does not look like a perfect thing for the fab. Okay, so a lot of weird stuff. I'm going to focus just on the fact it's got something called fractional statistics, and which has been finally shown after many years. But more interestingly is non-abelian fractional statistics, which turns out to be the idea where we can use for quantum computing. Now, some of these theoretically possible structures of non-abelian statistics support universal quantum computing with all the gates possible, but the ones we think we have are slightly less powerful than that, but still quite powerful. So the notion that this stuff, this non-abelian statistics could be used for quantum computing is due to Kitaev. And the idea is you've got these materials have these fractionally charged excitations, which are like little vortices, and if you move them around and braid them around each other, you end up, there's a hidden quantum information, I'll show in a second, and you process that. So what happens is, there's some of these defects, you can't make them locally. You can only make charge, in this material it has charge a quarter objects, but you can only make a charge a half object locally. But if you now can break up that object into two half objects, which are charge a quarter, which can't be created locally themselves, they leave a kind of entanglement pattern behind them. And you actually, the simplest case, you need 4 of these things. And this is enough to make a qubit, and the different entanglement patterns correspond to the qubit pointing up, sideways, down, etc. So by moving them around each other, you actually can process this information. But let's see if I can move forward a bit. Right. Okay, I'll come to, let's go back. So this is the information in the entanglement pattern is inaccessible to the environment, provided the things are sufficiently well separated compared to some microscopic length scale. And that's why the information can be hidden and processed, at least on paper, by this method. So it turned out that once this principle had been seen in the quantum mechanical problem, which was difficult in the quantum Hall problem, it was realized we can maybe do this in other systems too, this fractionalization. And this is actually the central part of the architecture, but I'm not sure whether we've seen the actual proof of the device that Microsoft announced earlier this year, the Majorana-based architecture for quantum computing. But let's see. So what's behind this? This is actually going back to my story about the spin chain. This is, in 1937, a lot of physicists are slightly strange. I don't claim not to be strange, but this one Majorana was a particularly brilliant but strange physicist. But he came up with he came up with the idea that you could basically write a complex object as a sum of a real plus an imaginary part. Which doesn't sound like a huge insight, but it was a huge insight in the quantum place that he applied it, because quantum states are usually complex, right? And if I take his thing is a qubit, which is a box, this orbital, which can either be empty or filled, and we have something called spin-orbit coupling to allow it to prevent the second electron from going in with other spin. What he showed is, his thing is that you can actually, if you put something, I'll show you in contact with a superconductor, you could actually break this orbital up into 2 half orbitals. And the information about whether it was filled or empty before you broke it up is hidden in the entanglement pattern. This is a kind of much wilder thing than the spin chain example I showed, but it's amazing. And there you are, you pull this apart, and to get the information out, you have to bring these things back together again, and then you can see whether they're filled or empty by measuring them. But in the meantime, by braiding them around each other, you've kind of manipulated this information, right? So anyway, this is the quantum physicist's beautiful dream that Microsoft has been trying to implement. of a topologically protected qubit. And I view it, on paper at least, it's actually a satisfying answer to the problem of scalability and robustness against decoherence that's needed for quantum computing, because because as practical people, technologists and entrepreneurs have to have some skepticism in believing all the beautiful dreams that the physicists tell them. But personally, I do believe it's a realistic dream which will be achieved at some point. And this is the scheme that where you put this stuff in contact with a wire. You have a nanowire, and you can formally write the electron operators in a nanowire in terms of their real and imaginary parts, which is shown in green and purple here. But what happens when you combine them with a superconductor is they split apart but recombine in such a way to leave half an orbital, a red and a green and a purple one on either side of the sample. Okay. Anyway, so that's one of the approaches. There are lots of other approaches to quantum computing with actually qubits which actually exist. The transmons, the superconducting qubits at IBM, nitrogen vacancy centers, ion traps, as in continuum and stuff. So these are actually getting better and better and better. But actually they're not just useful for quantum computing, they have many other uses besides information processing. Qubits are not just for quantum computing is a sort of a dream still. We think it seems to be approaching, but quantum technology is here. The size and sensitivity of these things to the environment makes them perfect as quantum centers. And indeed, the simplest one, the nitrogen vacancy in diamond, which I think there's probably going to be quite a lot of talking about here, allows ultra-high precision magnetic field measurements, which could be used in biomagnetic things such as brain imaging or geolocation. It turns out there's a fingerprint of the magnetic field at each point on the surface of the Earth, which, including the oceans, which could be used to set a kind of fingerprint to know where you are if you process it with AI. And not just electric and magnetic fields, gravitational fields can be exquisitely measured by quantum interference effects, acceleration. So a lot of the devices that we need could be miniaturized and made much more technically sophisticated and powerful, provided we can, bring all the stuff down into a simple package. So even if we are still waiting for the uses of quantum computing out of the qubits, which seems to be advancing, we actually have a lot of important technology today with quantum sensing. And as I say, many examples will be at the conference, but finding and developing niche quantum sensor applications will surely allow smaller players in many around the world to have access to play in this game, because quantum computers themselves, they've devolved to large governments and large corporation things. Possibly the Bengaluru Karnataka government thing is going to build a big enough one, but the actual quantum uses are growing and growing every day. And so actually the ability of countries to participate in this second quantum revolution is actually dependent on having a vibrant scientific culture in their universities where quantum literate researchers and future technologists are trained. And government investment in science education and in universities and institutes, and basically allowing them to participate in world-class science. It's important for any country to have at least one place where there's some world-class science is done, because that serves as an example to their young people who want to go into science to see when it's done. So such investment, I believe, will pay off many times over. So I hope I guess the minister is not here but I believe from what the words which are said at this conference is they understand that. And it produces a local culture where innovation in quantum technologies can flourish and startups happen and things. Okay, so the moral of all this is that three communities need to collaborate with each other in science. It's I do toy model building to try and understand where things can happen, but you need much more mathematically sophisticated people to understand why it happens, but most of all you need the cutting edge technology and material science to bring these things to a reality, otherwise they're just like pipe dreams on a piece of paper. And of course, apart from the scientists, you actually do need the entrepreneurs who have to look at this stuff and decide, is it really viable, or do I believe the dream that's being sold to me? And if it seems viable, they're the ones who've got to make it happen. And without all this coming together, we don't get this advances that we need. Okay? Oops. And finally, I think that was the end of my talk.
Thanks very much, Duncan, for taking us on this 100-year journey, and especially all the excitement that, and you alluded to Hamlet, all more things on heaven and earth, I guess, than we can dream of. But I think young people here, I hope this will inspire you to dream of.
Thank you, I couldn't remember the quote.
Inspire you to dream of many more things, and it's, as you said, the theorists who dream and experimentalists have to keep them also rooted and grounded, and in Bangalore we hope we can bring that and all the other communities that Duncan mentioned together and make it happen. So